Yeah, welcome after lunch. I hope you all are enjoying DEF CON so far. We have lined up good amount of talks, good quality talks, and just trying to add one more talk to the lineup. My name is Parth Goswami, and we'll be talking about adapting open source CNI plugins for IPAM. Now, before I talk, just wanted to have a quick check. How many of us are students over here? Quick raise of hands. All right. And for the experienced folks, how many of us are having networking background, like formal education or worked with networking? All right. Okay, cool. Thank you. Yeah, so again, don't quote me on this, but based on my experience, based on my observations, what I've seen is networking is often that aspect in the computation, which is often overlooked due to various other various facts. Like it may be complex to some of us, it may be, it might not make sense to some of us might not seem it very necessary as a necessary concept, right? So, but that's not the case. So you think from the bare metal point of view. You have bare metal, and then you add a hypervisor layer on top of it, right? And then on top of that, like the hypervisor can be type 1, type 2, and then you would have your virtual machines applications. That's the first case. The second case would be like you again have a bare metal hypervisor. Then in case of containerization, containerized environment, you have your container run times, and then you would come up with or you would spin your containers and then pods and lot many other stuff and the eventual applications, right? So the backbone of this entire stack in case A or case B is the networking. Without networking, you can't interact with outside external network or with like the processes running on the same within the same container or the same virtual machines. Even they would need networking, right? So we'll discover how and why they would require that. So this is just an attempt to simplify, to simplify networking and to maybe just try to burst some myths around networking to ensure that networking is not that as scary as it seems to some of us. So this is just an attempt into that, and I'm trying to simplify the concepts, trying to just give you a very high-level overview, a superficial review of the concepts that we are going to see and going to discuss today, right? So given this as context, the title is Adapting Open Source CNI Plugins for IPAM. So the approach that I'm going to follow today is we are going to dissect this title in the next half an hour, right? So first of all, we are going to understand what CNI is. Then we are going to understand what plugins are. Then we are going to understand what IPAM is. And then individually, we are going to weave together, combine together these three components, these three topics, and understand this entire topic as a whole, right? All are with me? Cool. So sit back, relax, enjoy the next 30 minutes of uninterrupted listening. No Spotify. Okay, cool. Next slide. Okay, so as I told, this is the agenda. CNI, CNI, IPAM, IPAM, some more IPAM, some more CNI, and then the actual main topic. So instead of getting directly into the topic, the focus would be to build the wall brick by brick, and then once we have a good complete overview, that is when I'll be revealing the topic, right? Next. All right, we'll start with the definition of CNI. So CNCF, all of us know CNCF. The textbook definition that CNCF gives for CNI is that it is a specification that defines how to configure networking for Linux containers. It does that by providing APIs for networking solutions to integrate with runtimes, right? So take a look at this pic and just try to imagine the pic from the top-down approach, the reverse approach. So at the bottom, you would have your runtime, your CRI, container runtime interface of your choice. It can be any CRI. On top of it sits the CNI. CNI ships lot many components, and these components are nothing but collection of codes and programs. So these components are called as plugins. So we'll also take a look at how exactly plugins are built and what plugins are. But as a very high level overview of architecture, you have CRI at the base, at the bottom, runtime of any choice. Then you have CNI on top of it, and then this CNI ships lots of plugins, right? Next. So if I'm talking about CNI, right? So container network, So CNI is like an interface for your network. So if I were to build my own CNI, and which I can very well do, it must perform some steps. It must have some capabilities, right? So this is kind of a very superficial, standardized steps that every CNI should follow. So let's say I have a container and I need to establish a network inside that container. So for that, I need to have a network namespace, right? So anybody here who can help me with the definition for network namespace? Anybody? Yeah, please. Okay, understood. Cool. Okay, so for all of you, there are again two concepts in this question. Network namespace, right? So namespace is one thing, and then network namespace is another thing. Namespace, I'll start with namespace, a simple definition. I'll start with a very layman explanation of that. So we are attending DEF CONF, we are sitting inside this building, we are attending this very talk, all of us, right? So if we are supposed to have another talk, host another talk, we have two options. Either we can have a similar talk, like not similar talk, but a talk parallelly, concurrently within the same building somehow, or we have to utilize other hardware, other infrastructure, other building. If it is in other building, that's fine. But if it is in the same building, then in that case, we should ensure that this talk is not interfering with the other talk. This talk is not influencing the other talk. This talk is not disturbing the other talk. So what did we do? We created segmentations. We compartmentalized this floor by creating walls, right? So we segmented them. So the process of segmenting, creating segregation is called as namespace in the Linux world. So namespace, the concept is taken from the Linux world, Linux architecture, and then it has been shipped or maybe imported into the containerization world as well. So every namespace will host a number of processes, jobs, and because they are in a segregated, isolated environment, they will have their own host names, they will have their own user policies, they will have their own file systems, they will have their own individual interface cards, and a lot of the stuff, right? So security policies. So those applications are sitting in on the same virtual machine or within the same containers. But we don't want every other application to be interacting or interfering with other parallelly running application. That is the reason we isolate them virtually. Everything is virtually. Extending this concept, now we need to do the same thing with the network. So thus network namespace, NET, right? So with network namespace, what we are doing is we are segregating the network. We are kind of isolating the network. So every individual network namespace within a cluster, even though it is in the same cluster, it will have its own network policies. It will have its own network interface card. It will have its own firewall D rules, IP table rules, and NF table rules, and it will have its own socket and port pairs. It will run like a network namespace may be running on X protocol, and another network namespace in the same cluster will be running on another protocol. So if I were to create or establish a network within a container, I need to come up with network namespace, right? So my CNI should be able to come up with many network namespaces within a cluster. Once that is done, then the CNI should be able to create a bridge between the host network namespace as well as the container network namespace. And then we will use some Ethernets to kind of help the container interact with the underlying host as well as the external network. Now, it is written as veth, right? So because we are at the container level, we are not at the bare metal or at the virtual machine level or at the physical device. So since it is containerized, everything is virtual. Every device you will see is virtual, and hence the Ethernet is the interface as well is a virtual Ethernet. And then you attach one end of that virtual Ethernet to a bridge and another to a network namespace, and then you assign the IP addresses, and that is when your interface comes up and your pod goes live, right? So this is some of the, like this is a sample code, a sample program, and this is a requirement for almost all the other runtimes. You call it, you talk about RKT, you talk about Mesos, Swarm, Kubernetes is there, like any CRIO is there, any runtime you talk about, they would require such sample code, such programs. Now, if I create a standardized bundle, a package it, and then ship it with every other container runtime, then I would start calling it as a plugin. So this is a plugin. Plugin is nothing but a collection of program, collection of code doing a specific task, right? Next. Yeah. So again, CNI, I can come up with my own CNI as long as it is following certain standards. So these are some of the most mandatory things or policies, or not policies, but activities the CNI should do, right? So for example, as I told that the CNI is supposed to create network namespaces. Similarly, like if I am coming with my own CNI, it should create, it should have the ability or capability to come up with its, create network namespaces. Once the network namespaces are created, obviously it won't be just one, there would be multiple. Then the CNI should be capable to identify that for a given container, which network namespace it should assign itself to. That is done, then it should be able to invoke the bridge when the container is getting added, or when the container is getting removed or maybe terminated. And then, yeah, whatever files we are going to come up with as part of configurations, it should follow a standard way, like JSON is the preferred format. And then, yeah, it should also provide us the ability to interact with the plugin. How do we interact? With the help of CLI. So the three basic commands that it should entertain is add, delete, and check. So the CNI should be able to interact with the plugin in order to add the container to a part of to a network namespace, delete the container from the network namespace, and check and verify if the container, the network is up or not, or if the connectivity is established in a proper manner or not. And then, yeah, so it also does the management of IP addresses. And once all is done, when I'm talking about the CLI commands, it should come back with a result in a very specified format. It can be, again, JSON, text, tabular, whatever the preferred format is. So the output should be provided to us. So this is some of the key capabilities, most mandatory capabilities that the CNI should do. Now, so far what we have seen is, again, a quick recap before we move on to the next concepts. So far what we have seen is the definition of CNI, the textbook definition given by CNCF. Then what exactly a plugin is, how a plugin is built. It is a collection of code and a program, or yeah, collection of program. And then these are some of the examples of plugins. So the entire talk is about adapting third-party plugins. So these are some of the built-in plugins in the first bullet point. Second are some of the third-party. I have a slide and I'll discuss this in a bit more detailed fashion. So yeah, next. Yeah, okay. So that was the first half, right? Second half is IPAM, IP address management. Now, I as a network admin or an architect, if I am dealing with any of the activities such as assigning IP address to a device or Ethernet, tracking the assigned IP addresses, managing the assigned IP addresses, monitoring the assigned IP addresses, revoking the IP addresses when there is no need, and releasing it back to its pool like carefully, right? So if I'm dealing with any of these operations, in that case, I am actually dealing with IPAM. IP address management. So it's not like you have a device, let's say it is virtual or physical, doesn't matter. You assign an IP address to that device and then you go on about your day. It's not that. You have to ensure that the device, whoever gets IP address, those IP addresses are tracked, they are monitored, they are governed, they are managed carefully, and then yeah, if there is if the pod or the container goes defunct, right? So in that case, you have to carefully revoke the IP addresses and release it back to the pool. So all of this requires a standard procedure, a methodical approach, a methodical system, and that is what is IP address management, right? So yeah, so it also integrates DHCP, and it is like a sophisticated integrated suite of tools. So one slide back, please. Yeah, so in this slide, I talked about IPAM in a very generalized, like simple IPAM, nothing related to Kubernetes. It is your general networking outside of your Kubernetes, like your bare metal and your normal networking, plain IPAM. In this slide, now I'm talking about IPAM from the Kubernetes perspective. So whatever concepts that we have discussed so far, right? The need to assign IP addresses, track, monitor, right? So again, Kubernetes is working at the cluster level. So Kubernetes itself exists because the containers, the number of containers grew beyond us, beyond a point where we couldn't manage as our as an individual. So that is the reason we need an orchestrator. So obviously it has to be in a cluster. So if there is a cluster, there would be nodes. Nodes can be of any combination: physical, bare metal, virtual machines. On top of that, there are thousands, millions, and yeah, n number of pods. So every pod is requiring a unique IP address. We know this. Services require IP addresses. There are a lot many resources in Kubernetes that require IP addresses. So Kubernetes cannot skip IPAM. It cannot step over IP address management. It relies on IP address management, right? So if it relies on IP address management, if it requires all the capabilities of managing, tracking, governing, assigning IP addresses, revoking, there must be someone who does it for Kubernetes. The answer is kubeproxy. Kubeproxy is a tool that handles the traffic IP address management for Kubernetes, but there are certain limitations. For example, it is good for small scale traffic, small scale cluster, but when you grow beyond a certain threshold, it becomes ineffective. Another thing is it provides the capability of load balancing between multiple pods and containers, but it is not intelligent in the way that if it doesn't track or monitor the pod's health or the pod's load and then divert the traffic accordingly. It doesn't do that. So kubeproxy is good, it's fine, but it doesn't, it's not enterprise ready, basically. That is how I would like to term it. And then, yeah, if your cluster or if your network grows beyond a certain threshold, certain limit, kubeproxy fails in such case. Again, one important point is it uses IP tables in the background. So the way IP tables work is you come up with IP table rule set, right? You add rules into the IP tables, and then based on the policies, your network would be traversed. So if your number of pods, networks, and the containers grow beyond a certain point, your IP tables start extending, start getting large, and it would take more and more time for the rules to get parsed, and that becomes slow. So basically, it is slowing down the entire network, the entire performance. So this is the reason why CNCF as an ecosystem started adopting or adapting third-party networking plugins, right? So we'll look at that again. Yeah, again. So IP address in general, IP address management in general, plain IP address management, then IP address management in Kubernetes. That is what we looked at in the last slide. Now, these are some of the so this is one of the main core pressing challenge with IP addresses is the IPv4 exhaustion, right? I am sure all of us are aware about it. Back in 1980s, when we came up with the concept of IPv4, we it is divided into 4 octets, right? 8-bit each. So that gave us millions and billions of IP addresses. So to be precise, 4.3 billion IP addresses, to be very precise. And then out of this many IP addresses, which are again divided into classes and ranges, some of them are reserved for, some of them are reserved as private IP addresses. Some of them are loopback, multicast, API, PA. So there are a lot many ranges and categories. So if you subtract all this reserved IP addresses from the 4.3 billion, so it gives you, so this IP addresses reserved categories is about like 500 million. So that gives you about 3.8 billion IP addresses, right? So back in 1980, the world thought that this many IP addresses would be sufficient, because that time the world used to think that IP addresses are used by persons, one IP address per person and not one IP address per device. But 10 to 15 years down the line, like 1990, 1995, it was very clear that no, IP addresses are used by devices, and individual can use multiple devices. Even on on an individual device, there are a lot many IP addresses. You just run IPA command, IPADDR command on your Linux terminal, and then it would give you the IP addresses attached to all the possible interface cards, right? So every device will consume multiple IP addresses, and that there are multiple IP addresses at the individual, multiple devices at the individual level. So extrapolate this concept and think from the enterprise perspective. Enterprises runs on clusters. Every cluster again is a combination of nodes, physical, virtual. They have millions and billions of pods. Every pod, as I told, requires unique IP address. Services are there, other resources are there. So basically IP address exhaustion is a very pressing issue, and the consequences are network congestion, security risk, difficulty in scaling, increased complexity. So for example, network congestion. So I have a pool of 100 IP address. Since the pool is limited, the pods that are getting generated or going to get generated, they would try to have or get assigned to an IP address, and if they fail, then the traffic, the request that is coming in, that would fail. So that would create some congestion in the network. Next is security risk. Again, because of the limited IP addresses that you have, the network admin might be tempted to reuse the IP address and assign it to other pod. Meaning, let's say there was a pod that went defunction. So before the IP address could have properly revoked and released back to the pool, network admin assigned it to some other pod, right? So now, since it was assigned to some other pod before it got released properly, there is a live access to the pod's sensitive information, and that possesses a security threat. Next is difficulty in scaling. Again, I have a 100 IP pool. My requirement is 400 IP. It becomes difficult for me after a certain extent to basically assign those IP addresses, right? And then increased complexity. So if a network admin is provided with a limited set of IP address to begin with, then they would try to adopt some innovative solutions like overlay networks or like NATing, and that makes the entire networking architecture a bit complex. Yeah. Similarly, Kubernetes also uses network plugins, and then, yeah, some of the built-in plugins are host local and DHCP. Now, these are the built-in plugins. So host local is nothing but your plugin is kind of natively assigning IP addresses from the predefined pool and like establishing network within your container. This is good for small scale, but again, if you're going for a large scale cluster, it won't make sense. DHCP, on the other hand, it is good for large scale, but again, it uses or it has to like we have to establish a DHCP server as well who would track all those IP addresses, and that's an overhead. So we as architect don't want that overhead with us. So the built-in plugins are there given by Kubernetes, and then there are certain limitations with each of those built-in plugins, and that is how, and that is why Kubernetes started supporting third-party IPAM plugins. And now in the next slide, let us see what those are. Yeah. So this is the glossary of the network plugins. On the left-hand side, you have the basic kind of built-in network plugins that is shipped with your Minikube or your Kubernetes cluster. And then on the right-hand side, you have the third-party, completely open source, fully open source solutions in terms of your networking challenges like network congestion, scaling issue, right? Security issues, right? So we'll take a look at that. Bridge, again, bridge is a concept that was defined or devised in Linux, and then it creates a bridge between, so this bridge IPAM plugin, it basically creates a bridge between your Linux containers and the host device, right? So that the communication can get established. And then bridge IPAM, the bridge IPAM plugin also uses either DHCP way to assign the IP addresses or host local, which we saw in the previous slide, and again it is mentioned over here. So host local and DHCP are the two ways through which bridge IPAM plugin can assign the IP addresses. And it is widely used, at the individual level or where you don't have any production environment running. Bridge is often used as a networking plugin. Next is host local. Again, as I told, it is good for small scale because it is using and assigning IP addresses from a predefined pool of IPs. But when you try to scale it up, it's not going to be efficient. Next is MAC VLAN. This is an interesting one. MAC VLAN is kind of providing unique MAC addresses to your interfaces, to your containers, so that they would start behaving as if they are a physical device, physical interface. So so MAC VLAN is again a powerful solution. IP VLAN is similar to Mac VLAN, although it differs in the way that it uses less resources, and then it provides a single MAC address to multiple pods, to multiple containers. Loopback is, I am sure all of us know the address of loopback, 127.0.0.1. So it is an extremely important interface. Why? Because some of the applications are built in a way that they assume that there is a loopback interface. So even if they don't actively require it, but if they don't find a loopback interface running, the application would not generate the result, or it would come up with the logs saying that IP, like the loopback interface not found. And then there are lot many jobs, lot many processes that are programmed in such a way that they need to talk to each other, or they need to talk to itself through, and they do this communication through the loopback interface. Next is static and DHCP. Static is like you statically assign an IP address. Usually, like for those who are in college, in your local lab setup, you basically would do this. You statically assign an IP address that might not give you the ability to interact with the outside world, but yes, that you at least have an IP address. Again, as a solution for that, an alternative is DHCP. You dynamically assign IP addresses, but as I told, it needs a DHCP server, and that is an additional overhead, right? So these are the challenges, limitations of the built-in native IPAM plugins. As a solution, there are many projects, many communities that came up with the solution, right? So some of them are listed over here. Again, this is not an exhaustive list. Flannel is a lightweight third-party IPAM plugin used for, again, small-scale clusters. Like for large clusters, there are other options. Calico, I have worked on Calico, and I've been using Calico for a long time, and it is kind of a networking solution as well as a security solution. So that's another IPAM plugin. Next is Cilium. It uses eBPF protocol to give you enhanced networking results, performance basically. Next is Weave. It is into mesh networking. And there is another one which I missed to write, is Canal, CANAL. Basically, it's the combination of Flannel and Calico. So, the Canal IPAM plugin uses Flannel's networking capabilities and Calico's security policies. Next is SROV. It is widely used, again, for high performance. OVN is Open Virtual Network for Kubernetes. It is basically used in such cases where you would need advanced networking features. So yeah, this is again not an exhaustive list. All of them are open source. Please log into their respective community pages and see if in any way you can contribute and strengthen the third-party IPAM plugins in any way. Next. Yeah, again, a quick recap. We started this talk with the concept of CNI, what exactly a container network interface is, why it is used, why it exists, how it can be built, if we are supposed to build, what needs to be done. Next is importance of CNI, IPAM. We got introduced to the concept of IP address management, both without, like in absence of containerized environment and within containerized environment, and what are the challenges presented by IP exhaustion, what IP exhaustion exactly is, and then open source CNI plugins, and why CNCF for Kubernetes is adapting this third-party solutions. Now, when I am saying third-party solutions, what exactly I mean is, or why I'm referring to them as third-party, is because it is not the CNCF or the Kubernetes project who is managing and kind of governing these third-party solutions. These are managed and governed by their respective projects, by the respective communities, which are open source. And hence, even though they are open source, they are not native to Kubernetes. They are native to cloud. They are native to cloud computing, but not to Kubernetes, right? So, so that's the case that they are third-party, but yes, widely used. And yeah, next. Yeah, I think I am yet to introduce myself formally. So I'm Parth Goswami. If you ask what I do, my wife would say that I'm a cluster wala. Basically, so she thinks that I would sit in my home office entire day and keep on building clusters. That's definitely not the case. I work as a customer enablement engineer at Cloudera. I help our customers to get enabled on our products. Cloudera itself is built on a very large, robust suite of Apache open source projects. And yeah, so I basically enable my customers to get acquainted with the products, train them, and a very small subset of my role requires building clusters. But yeah, yeah, and then I write my blogs, my findings, my thoughts on this website. And yeah, thank you so much for your time. Any questions? Yes, please.
Hi, thank you for your session. So actually, I wanted to ask you one question, which is like a comparison between Calico and Cilium, because you see with managed Kubernetes, all three clouds are right now implementing their CNI with Cilium. But when it comes to bootstrap clusters on private cloud, let's say OpenStack, I have done some study between the two when especially comparing the Calico with eBPF data plane enabled. So can you give me a comparison between Cilium and Calico with the data plane enabled? Which one would you say? Because I want to avoid the overhead of the kube proxy, which is there without the data plane.
Understood. So I'll start answering your questions from reverse. So if you're using any of the third-party solution, you are kind of negating and stepping over kube proxy. So don't have to worry about that to begin with. That's the first thing. Second is Cilium uses eBPF a lot, and that's the reason if you're specifically focused on the network performance, in that sense, Cilium would make some sense to you. Cilium would be should be your appropriate choice. Calico also implements eBPF, but not as efficiently as Cilium, right? And I have personally worked with Calico for over 2 years. I have been a Calico community ambassador for over 2 years. So I am not very much exposed to Cilium as to how it works and what exactly the differences are there in terms of performance. So won't be able to justify your question with the very proper answer. But yes, if you're worried about the optimal network performance, go with Cilium. But if you are looking for something advanced than just mere kube proxy, looking for security, like if you want to ensure that your traffic is authenticated and not authenticated but encapsulated, then in that case you can go for Calico as well, because security wise Calico is good, performance wise Cilium is good. So that's the basic answer to this.
Got it. Thank you for your advice.
Yeah. More questions, please? Yes, please. At the back.
So if there are two build pod assigned to same node, and suppose one is taking a lot of network resources, right? It is network heavy. So network bandwidth is shared or it is totally isolated on the Kubernetes?
This is a very typical architectural point of view question. I mean, it entirely depends upon how you have designed your architecture, how you have defined your rules in, like if you're using IP tables, NF tables or firewalls, or you are using it, what kind of plugin you're using it. Again, as I told, kube proxy is not intelligent load balancer. So it would not check or monitor your pod's health, your container's health, and it would just keep on diverting the traffic. But if you're looking for any of the third-party intelligent load balance based solutions, in that case you should be able to get step over this. But again, I will be able to answer this only after understanding how the networking is being implemented.
But that can be done, right? If you want to implement, there can be proper isolation at the port level?
Yes, exactly. Yes. So at the port level, basically what you can do is, even if you don't want to get into isolating your ports, you can come up with a pair of port and socket, right? So like with the same port, if you are mapping it with a different socket, it's like a different pair, and then you can divert the traffic on that basis as well. So if you are lazy enough to not isolate, or if you want to isolate, that's fine. But if you not want to isolate, you can play with the port and socket as well. So that is again another like solution or workaround rather. More questions, please? Yes, please.
Yeah, hi, I am the engineering manager for OVN Kubernetes.
Yeah.
And generally it's perceived that OVN Kubernetes is for enterprise level. That's why OpenShift is using OVN Kubernetes as a default plugin for that. But in your view, have you seen OVN Kubernetes as only an enterprise, or can it be used in small scale as well?
The benefit of using OVM is, if I am someone who is working with a small scale cluster, but looking for advanced features, networking features. In that case, my by default choice would be OVN. Now, if I am using or require with advanced networking features, that doesn't necessarily mean I am working in a large scale cluster. So my requirement is if it is around something advanced, then doesn't matter what the scale of my cluster or my architecture is, OVM would be my choice. Yeah, but I have not seen, because I'm not, again, not exposed to all of this networking plugins. It won't be possible. But yes, so from the limited articles that I read on Medium and here and there, so this is what my basic understanding is. Yeah, yeah. Good to have you, by the way.